So yeah, we'll talk about juvenile fish guidance at hydro stations for most of the conversation, and then a few minutes on getting adults. I've spent most of my career getting adults over dams and juveniles over dams, but then once we get them over the big dams, can we get the fish to the suburbs where they actually reproduce and create the next generation? So that's the upstream passage. All my career, I've learned that we need to work together as engineers and biologists to figure out behavior of these species, and then the engineering fix. And I've worked for utilities, since 2001. And so I kind of joke that my job is to keep engineers out of jail, because engineers are always building things and we need to think about the fish also. So I'll just jump into the presentation and we can take questions at the end. So the two sections of the talk. Part one is a downstream fish passage, specifically a behavioral guidance system. And I'll get into the details on that. This is just kind of the picture. The first one developed our U.S. Army Corps of Engineers, company I work with now. I consult to as their science advisor. In 2005 and 6, they tested this floating wall. That's as simple as it is at Bonneville Dam, the lowest dam on the Columbia River. And that part two, I'll spend a few minutes on the culvert passage. So on downstream passage, getting juveniles downstream is our big problem. How do we do that? I think upstream passage with trap and haul with fish ladders is a mature science, but it's that downstream passage. So we start with two questions. Fortunately, here on the Columbia River, I'm the science advisor for over 100 utilities that buy the power from Grand Coulee on down to Bonneville. And so I'm responsible for kind of explaining what we're doing on the river to the power companies that pay for everything, advising on if money is well spent, where's the best area we can save our dollars. So they're very goal oriented. There's a very business overlay in this management of fisheries on the Columbia River. And so first question is, what are your conservation goals? Quite often a regulator will come in and say, just more or better survival. Well, that my interpretation, your interpretation may be two different things, but if we could agree on a conservation goal, then we have that's something to work towards. Like right now on the Columbia River Dam, Snake and Columbia River, we have a 96% juvenile survival through all routes. You put 100 juveniles above Bonneville Dam, you get 96 below. Turbine passage, spillway passage, bypass, locks. So it's a combination of all those. So how this behavioral fish guidance system was developed was to increase the number of fish that go through a safer route of passage to meet that 96%. So once you have your conservation goals, if possible, what are the available technologies for that work? So I'm going to watch the clock here. So you first need to kind of big picture understand the behavior of fish. And I've had the opportunity of working on some of the largest fish passage, fish guidance projects in the world, development of different types of passive and active tags. It's real fortunate the opportunities we've had to do the science, and I enjoy sharing it with people around the world, like this opportunity. But from these evaluations, we have many reports, many evaluations on several, mostly Pacific salmon species. And it's a lot of it is kind of common sense, but it's nice to quantify that. Fish downstream migrants, including adults, generally follow a bulk flow. They go with the flow. They're surface oriented, kind of take advantage of that higher water velocity, and they cue on flow and turbulence. This is some of the first research out there, is what signals to a fish to go to what area, what depth, what direction is flow and turbulence, and then responses to water quality and quantity. You get a freshet, a storm, rainstorm, cold, muddy water comes through, and that often convinces a fish it's time to move. But in a dam system, those migratory cues are disrupted. So don't get caught up on the details here. This is just some of the systems we've used on the Columbia River in the Pacific Northwest, United States. Is these spillway passage is a passive system, but you spill water over spillways. That's water not going through turbines, so there's a cost there. And then there's these large floating surface collectors, hundreds of millions of dollars. This barge artificially creates a current, collects juvenile salmon in here. They're put on a truck and they're driven down to below a dam. Very expensive, and their technology really isn't proven. And then on our dams, we're using existing systems to divert juvenile fish and adult fish out of turbine intakes and put them through ice and trash sluiceways, and then move them safely downstream. So these are some of the physical systems we have. Some of the non-physical guidance are strobe lights, acoustic deterrents, bubble curtains, and there's pluses and minuses with each one of these technologies. So working with the U.S. Army Corps of Engineers and barrier manufacturers came up with an idea of a behavioral fish guidance system. And there at the top right is an example. It's very simple. There was a large debris barrier at Lower Granite Dam on the Snake River, the first run-of-river dam on the Snake. And it seemed that juvenile fish were swimming along that towards a spillway. So this, after many, many years of observations, decided to create a barrier specifically to guide fish. And that's what we'll talk about more today. And these are just examples of, this is boat barrier, but this is the fish guidance system here. We'll get into the concept behind I'll just call it FGS. It's easy. FGS is it's a physical barrier. It's only about 3 meters deep, and it doesn't block fish. It's a behavioral guidance. So it's a physical barrier that you get a kind of acoustic reflection off that as water flows against it. Yeah, it's a visual barrier, and then the hydraulic barrier. So all these three things work together. And then the most important factor is where you locate this barrier. So this is just a high-level example. This is Snake River, very big river in eastern Washington, but the concept is the same. Your reservoirs on the right, spillway and Powerhouse. The way we manage the system is try to get more fish to the spillway, which is our safest route of passage. So these are kind of old 1990s graphics, but I'm a biologist, not Disney. As fish move downstream, water stops flowing, and you start getting them wander back and forth looking for an exit route. So these are kind of areas of flow we've developed and called over time just for communication purposes. So our intermediate zone is where water moves back and forth depending on spillway, spill, and Powerhouse generation. So you get a kind of a fluctuation. And then you have the flow net. And the flow net is the bulk flow into that specific route of passage. There's others, but we'll focus on these two. So you're looking for, and this is important to research, is a zone of separation. So in general, fish on this side of the zone of separation will go down the spillway. This side will go through the Powerhouse. So how do we modify the zone of separation? And that's the whole concept behind the behavioral fish guidance system. You put the wall in here, and then as fish come downstream, if they're on this side of the river, they have a reason to go to the north in this example and stay out of this turbine flow net. So it's a simple concept, but how you locate this is the most important part of the project. And here's actual results of that very first evaluation at Lower Granite Dam. This was a 60-foot deep barrier. We didn't know at the time, and real complex system. There's a high level, but what we found is 80% of the fish that contacted or approached the FGS were guided, and it reduced turbine entrainment 16% and helped us get to our Endangered Species Act required 96% juvenile survival. So I'll just give you several examples. This is Bonneville Dam. This is the actual first real evaluation of the fish guidance system in 2005 and 6. Very complex system, 2 powerhouses. And the idea here was to, you can see a spillway here. It's an old ice and trash sluiceway that the Corps developed to safely pass fish out of the Powerhouse 2 spillway. Now, this was before I worked on the project. I saw it as a utility biologist. I thought, boy, this is great. We can guide more fish out of the powerhouse, maybe produce more power, get higher fish survival. So it's a win-win. But the Corps decided to put the FGS in the middle of the Forebay as opposed to terminating right here at the entrance of the safe bypass. And I think the thought was just general guidance. Do we get guidance? So just a research level project. So this is a little better. It's about 700 feet long. And I apologize, I work a lot with Europeans and New Zealanders and Australians and go back and forth between standard and metric, but can't think that fast sometimes. It's still a little early and only got 1 coffee in me. So what we found this evaluation is guidance for a specific species, a yearling or spring Chinook, was approved by 15%. So 50% fewer fish went through a powerhouse before this was installed. And those that contacted this were twice as likely to even travel this whole distance, even though the bulk flows in the powerhouse, but were more likely to go into that bypass system. Now on this, there were 42 different anchors left and right of this to keep it perfectly straight. I was working with a mechanical engineer and she wanted it straight. And I said the anchors are going to be a problem, and it caught debris and there was issues. So we took it out after the 2-year evaluation. But we demonstrated that it did work. So after that, we started working on other projects. And that's when I joined forces with Worthington Products out of Canton, Ohio, that manufactures this. And so I'm their science advisor. We're talking with many other utilities in North America. And this is a Cowlitz Falls Dam in Washington State. This is where I started out at Tacoma Power. And small reservoir drops into 2 large reservoirs with high head dams. So the thought was, if we collect juvenile Pacific salmon in the small reservoir, we could truck them down and avoid those problems in 2 high head reservoirs. So this was the proposed configuration of the fish guidance system. And then they would go through a screen system and then a bunch of pipes and pools, and then be loaded on a truck at the downstream transport facility and then driven downstream. So the idea was, can we successfully get fish to this side of the river with a fish guidance system? So this is the conceptual. This was the actual study. This is a simple weir that we use to collect fish all over the state. This is the fish guidance system. And fish were actively tagged, JSAT tags, antennas everywhere. And the idea is, could we get juveniles in this area so the flow's coming at you? And this is called a heat map, frequency distribution, of where juvenile fish were observed during the outmigration. We could see they were focused in this area. So we were able to successfully move fish from one side of the river to the other. And today Tacoma has built that surface collector and it's working fine. So we jump to the East Coast with Atlantic salmon. So the Atlantic salmon are very similar. They actually used to be in the same genus as our steelhead on the West Coast. So they're more likely to, they're a little larger when they outmigrate than our Pacific salmon, more surface oriented, easier to guide. So this is on the Kennebec River in Maine, and it's to guide Atlantic salmon out of this head race. I could back up a bit. Main River, Kennebec River is on the side here, and there's a head gates, and then this head race, and there's no way for fish to get out of this area, Powerhouse is here, unless they back up and go upstream and come back around. So the idea was to put a fish guidance system here, and then an outfall So this is what the first prototype looked like. And this is the outfall. So they cut this notch in the dam and are able to put in an adjustable weir to modify the amount of water. You may not need full flow all the time. And there's Powerhouse right here. We get 75% guidance on Atlantic salmon on this project. I was pleasantly surprised it was that high. So it's a very successful project. This is another Brookfield renewable energy project on the Kennebec River farther upstream. This is a real complex dam. So the river flows this way, an island, another dam. And so anchor here, and the idea is to guide Powerhouse spillway, but there's a real nice sluiceway here. Can we get fish from the Powerhouse into that sluiceway? So this is what the system looked like. The concept of the behavioral guidance system is a 3 meter or about that deep wall, but with different flotation depending on the hydrology of the site. And that's where the engineers and design folks come in. This is a 27 cubic meter anchor to hold the system in place. It's a massive system. And so there's a Powerhouse intake spillway, and this is a sluiceway. And this was a successful project. I haven't received an update, but it's been there about 10 years now. So just summarize the behavioral fish guidance system. We have several other projects. We did tests in California. Let's see, where else? Connecticut River. There's 2 projects in California. So I could give all kinds of details on those. But that's just kind of overview of the concept, the technology, the application of the fish guidance system. The most important part of the FGS is the location. So we can design a barrier to stay pretty much anywhere. Worthington, they've designed a 3.5-mile barrier on the Amazon River, a big debris barrier above Juvenile Dam. So the engineering is possible. It's really the location of that fish guidance system. So do we know the behavior, species of fish, the behavior of fish that we're working with, life stages, all very important. And then where you locate that fish guidance system. And the benefit is you can actually add panels, subtract panels, move anchors to increase the effectiveness of the system. And what we found is it does modify fish migration behavior. We can move fish from one side of a river to the other. Like I said, it's not a complete barrier, but we can modify, especially salmonids and the river herring like shad. What species would they be? Bluebacks, American shad. The holy grail of fish guidance anymore, in my mind, are eels. Now, eels have a very complex life history, very complex downstream migration behavior. There may be some benefit of the behavioral fish guidance system, but that's kind of next area of focus and study are the eels. But with salmonids and clupids, herrings, we can move those within reason to a more safe bypass. It's a permanent physical structure in our regulatory arena in the United States. The regulators don't like to rely on management actions like modified dam operations and like that. If you could put in a physical structure, that's what they like the best. Now, it's usually a combination of 2, modifying spill, turbine operations, and then putting in a physical structure. And then a flexible configuration. If you're not meeting your conservation goals, you can add, subtract, as I mentioned earlier, modify, put 2 systems in, debris combination with a debris barrier. So it's very almost an infinite configuration at sites. But the more information you have at the beginning on your fish and hydrology, the more successful you'll be on your first application. So I think we're going to part 2, and we will have quite a bit of time at the end of this to answer questions. And if I can't get you the answer now, I can get your contact info and definitely follow up. So most of my career has been getting fish over dams, but we have a problem with what happens when they get to these smaller tributaries. Here in Washington State, so our Columbia River Basin, just to give an example of what we're dealing with geography-wise, our Columbia River Basin is about the size of France. So that's the area where I live, where I'm working in. That's not Puget Sound, Seattle area, but this is Eastern Washington, Idaho, Montana, Oregon. So we have this massive watershed, and then add that to Puget Sound, we have about 19,000 fish barriers just in Washington State. 84% of them are culverts and bridge systems, so not dams. And we're focusing on these, but it's kind of the new frontier in fish passage. We're getting fish past the big dams, but then now what? You'd hate to spend $100 million on a fish ladder modification at Bonneville Dam, and then the juveniles not be able to get to the creek outside my window here because of some foolish culvert. So with culverts, box culverts, other type conveyances like this, you have high water velocities, shallow water, laminar flow, steep gradients, and those all work together to form a passage barrier. And typically we're dealing with higher flows during spawning season. So you preclude fish from moving through these conveyances at times. So solutions, the ideal is to remove the culvert, bridge the system, and make a more natural bank width type passage. But as I mentioned, we have several thousand culverts in just Washington State, and they're never going to be all fixed. So you could do different culvert modifications. Lots of things you can do, but smaller projects on site, proven technology are culvert baffles or weirs. I'll just call them baffles. It's an old technology. There's been a lot of work on solid baffles, on how they modify the flows. They slow velocities, create resting pools, just create better environment for particularly salmonids or trout and salmon. That's really the focus in North America, or trout and salmon. But also, if you can pool water in summertime and lower flow times, you could get crayfish and smaller resident fish through. In New Zealand, the fellow that invented these, Kelly Hughes, in New Zealand, it's low flow is the problem during most seasons. They have a lot of freshwater shrimp and galaxids. They're a small fish, and that's been his focus. This is an example of an installation in New Zealand. We're trying to slow the water enough to get these smaller aquatic organisms past the culvert. In North America, it's mostly salmonids and larger fish at higher flows, but the technology still works. So there's been years and years of evaluation for solid baffles. There's been all kinds of different configurations, but there's been a hesitancy to install them in all the culverts because there's just problems with them. They're expensive. Big one is retained debris, and they're difficult to maintain. Getting in here and cleaning out rocks and logs is just dangerous and expensive, and we just don't have the resources to maintain these. So that's where we came up with this flexible baffle. Similar benefits to solid, but they can be a permanent. So they're so inexpensive, they can be a temporary or permanent installation. You can install them in concrete, corrugated metal pipes, plastic, HDPE. It's just a matter of the fixings, how the attachment. They're much less expensive than steel, stainless steel, concrete systems. They're easy to install and modify. You can, in a typical 10-meter culvert, you can install baffles in a few hours. It's very simple. And these do not retain debris. At about 3 feet, they bend over, 3 feet of water, meter of water, they bend over, and allow bed load to move through, big positive. And also many of our culverts are undersized because at the time we may have not have known the flow, and because of cost, we always kind of err on the side of a smaller culvert. So as these bend over, as these Flexi Baffles bend over, it preserves hydraulic capacity of that culvert. So this is simply what it looks like. The current material is Santoprene we use. It's the same material around the seals on your car doors and trunks. It's completely food safe, used for a lot of rainwater collection systems. It's an extruded. We can use a flat baffle, like here the fellow on the left is using, and put on a flat bottom culvert, or we cut these slices in there to make it more like an iris and install in culverts. And so what we do is kind of like to call it a prescription is, for instance, I'm working on a big project right now in the state of Alaska. They have a 600-foot long culvert. That's about 1.2% gradient. And we have the different flows, and we want to meet about 4 feet, little over a meter per second water velocities. We want to slow the water to that speed to allow Pacific salmon to migrate through. So we look at what baffle configuration will meet that criteria. And it's still kind of art and professional judgment right now on the ideal conditions. But for this project, for instance, you have up to 3 meter water velocities, 3 meter per second water velocities at times, and fish still do get through. So some kind of baffles will improve passage, will kind of expand the time that fish can pass through this culvert, and help kickstart that population. So we write a prescription on spacing of baffles, and then recommendations on how they're installed, what kind of fixing methods. And this is a little closer look at what the baffle looks like. And if you're in a concrete, we use a wedge anchor, pre-drilled, and then tapped in and tightened about 6 to 8 inch along the face. Or if you're in corrugated metal pipe or plastic, you just use self-tapping screws. And quite often you get these at your local hardware store. Very simple installation. You hammer drill, tap in the fixings, and this is what Flexi Baffle looks like after installation. And this is just a real quick picture of the different kinds of configurations we've had in the past. Brown culvert, square, oval, elliptical, and a real exciting happening that we're working on now is we've teamed with a company that can actually do computational fluid dynamic modeling of a culvert before we put the baffles in. So we can actually demonstrate to a client hydraulically what those baffles will do in their culvert at their specified flows. So this is just a generic output of an installation in New Zealand. So what we're seeing is this is about 0.3 meters per second, so a foot per second. This is our goal in North America and in New Zealand at the moment. We want water velocities at that 0.3 or a foot per second or below, to support fish passage. And the lighter the color, the faster. And I'll get into some more details. So this is actually a project in Alaska. This is the actual culvert we're working with. We place baffles about every 10 feet, and we leave a 1 foot gap over on one side to allow fish to move around. So this is a slice about 2/3 through this culvert at this water flow. And what we see, so these are meters per second. So what we see is you're below and still trying to work on the 0.3. It's just a matter of setting up this scale. But we see that we're meter a 1 foot per second in most of the run. This is 3 meters between baffles. But then there's a 1 foot area that is a little higher, but salmon burst speed, we're looking at pink salmon and chum salmon, that they can burst around this 1 foot space. And then at higher flows, we see that, sorry, I made one mistake. I should have had we can actually model before baffles, and the water is only just over, so this is 1,500 millimeters, 1,800 millimeters without the baffles, and it's, all red, 3 meters per second velocity. So it's about this deep and all red, 3 meters per second. But with these baffles, these plastic baffles at this flow, you're not seeing anything over 2.5, but you definitely see along the bottom where fish are passing. And for this specific project, they want less than 4 meters or 4 feet per second, a meter and some. So anything green, actually light green and below, meets their fish passage goals. So with this spacing, and if you want to improve this, we can now, and that's what I'm working with a client right now, is we can move these baffles even closer to see if there's a benefit of adding more baffles and expanding the good passage conditions. So just a quick summary on the baffles, they improve fish passage conditions. There's I think if you get over 5-6% gradient in a culvert, I think, you could put as many baffles as you want. I think you're just going to have trouble with any kind of fish passage through that. Maybe some like steelhead, some of your strongest swimmers. This is a temporary or permanent installation. I've had conversations with people where a project is budgeted for 5 years from now. Why don't you put baffles in now and get a kickstart on improving passage? And these are so inexpensive, but they're in good condition. You can just unscrew them, pull them right out, and use them someplace else. They're inexpensive, easy to modify and install. Say you put them in at 10-foot spacing, and you're not quite seeing what you want. With our CFD modeling, we can show you what can happen mathematically. But say you want to add a small section in the middle, or modify for a new species. You could go in and add more. You could change the angles, so there's almost infinite way of modifying these. And then they don't retain debris and preserve hydraulic capacity, bend over as water comes up. So that's a huge benefit. So maintenance is near zero. We recommend that owners go in and just take a look. We had a project in New York, in the state of New York, on the East Coast, that Department of Environmental Conservation is actually tagging trout to see if they're moving through this culvert. One of the baffles pulled out during a high flow event. The concrete was bad, so we just recommended using a deeper wedge anchor, and they were able to install it back in a few minutes and continue their study. So with that, I think we're done, and we have plenty of time for questions.